Video 3-2, looking at atomic dimensions, properties of atoms and ions, designating isotopes, elements on the periodic table, and average atomic mass. Okay, so, atomic dimensions, how big are atoms? Okay, and how big are the particles that make them up? So, our particles, okay, electrons, protons, neutrons. The symbol for these things, okay, you can write each one of these things two ways. E for electron, P for proton, N for neutron. The charges are superscripts, so minus, positive, and 0, or also known as not, N-A-U-G-H-T. Okay. Now, the other way you can do it is you write numbers on the left side. Okay. Relative charges, meaning the charges relative to each other. Protons and electrons, even though they're different sizes, their charges are basically just opposites but of the same magnitude. Okay. And notice the charge becomes the bottom number. And no charge for the neutron goes on the 0. Now, the mass number. Okay, electrons do have mass, but we assign them a mass number of 0, and those become the top numbers. Protons mass number of 1, neutrons mass number of 1. Okay, relative masses in a unit called an AMU. Okay, we see here electrons do have a mass even though they have a mass number of 0, pretty small, 0.00054866. Protons and neutrons, even though they have the same mass number, their masses are slightly different. Okay, 1.008665 and 1.007276. So neutrons are slightly larger than the protons. Okay, their actual masses in terms of units that you know of, kilograms. Okay, electrons, pretty small, about an order of 10 to the 4th. 9.1 10 to the 4th smaller than protons. Okay, 9.109 times 10 to the negative 31st. Protons, 1.673 times 10 to the negative 27th. Okay, neutrons, slightly larger again. Okay, now, how big are atoms? What are their sizes? Atomic radii from the center to the edge of the atom varies from 40 to 270 picometers. Don't forget, a picometer is 1 times 10 to the negative 12th of a meter. Okay, so really small. The nucleus, really, really small, okay, compared to the size of the atom, 0.001 picometers. Okay, nuclear density, though. Okay, if you were to just take a whole bunch of nuclei, tack them into 1 cubic centimeter, 1 ml, the whole thing would weigh 2 times 10 to the 8th metric tons. Okay, so 1 cubic centimeter of anything doesn't weigh that much, pretty much because the atom is mostly empty space. Okay? So the atom itself, not a high density, but the nucleus, really high density. Okay? Now, this thing, an AMU, what is it? It's an atomic mass unit. It is defined as 1.660540 times 10 to the negative 27 kilograms. Okay? Now, why define something as this weird number here? Why not just call it 1 times 10 to the negative 27 kilograms? Okay, so what's the basis for this? Okay, well, we'll come back to that in a second. Let's look at properties of atoms and ions. Okay, now, atomic numbers, and if you ever see something that tells you Z is equal to a number, let's say Z was equal to 4, they were telling you that for this particular atom, the number of protons was equal to 4. Okay. The mass number is equal to the number of protons plus neutrons in an atom. Okay. Sometimes they refer to as the number of nucleons. What's a nucleon? It's basically just a particle in the nucleus. Okay. Isotopes. If atoms are isotopes of each other, they have to be the same element. Okay. You cannot have isotopes of different elements. They have to be the same elements, which means they have to have the same number of protons. Okay. But what makes them different from each other is because they have different masses. So they are going to have the same number of protons but different numbers of neutrons. Okay. An ion is an atom that has a charge to it. The reason why it has a charge, protons and the electrons are not equal in that atom. Okay? And to figure out the charge, take the proton, subtract the number of electrons, okay? And look at the charge. Will be the same, will have the correct sign. In other words, if you have more electrons than protons, you come out with a negative number. Okay? So the charge will have the appropriate sign when you do it this way. Okay? Atoms can only turn into ions by gaining or losing electrons. Okay? Why can't you play with the number of protons? Well, if you change the number of protons, you just change the atom. It's now a different element. So the only way the atom can still be the same atom but turn into an ion is by playing with the number of electrons. Okay. Now, general terms for positive and negative ions. This one right here is not called a cation. This is called a cation. Okay, and you can remember it kind of like this. Okay, that is not a dead cat. That's a cation. Okay. Negative ions, anything with a negative charge, these are called anions. Okay, designating isotopes. Two ways you can write the symbols for an isotope. Okay, you can't just simply, if you have two atoms with their different isotopes, you can't just simply write their symbols because they're both going to be the exact same element. Okay, so one way you do it is write the name, or you can just simply write the symbol, right, and with a hyphen, and then you write in the mass number. Okay. The second way is to write out the symbol for the element, write out the mass number as a superscript to the left, and the atomic number on the bottom. Okay, so a couple examples. Okay, hydrogen has 3 isotopes to it, and not every element that has isotopes has names for them, but hydrogen does. So protium, deuterium, and tritium. Okay, now they all have to be hydrogen, so they all have to have the same name or the same symbol. So you can write it as hydrogen-1 or H-1. Deuterium, whoops. The other way to write it is because hydrogen has an atomic number 1, and this is the mass number, it goes on the top, okay, and the symbol H. Deuterium is hydrogen 2, and again, this is the mass number, so it has to go on the top. It's still hydrogen, so it has the same symbol and the same bottom number. All these isotopes have to have the same bottom number, same atomic number. Okay, and tritium is hydrogen 3. So it's going to be 3/1H. Okay. Now, how many neutrons in each isotope? Okay, don't forget, this is the mass number. This is the protons plus the neutrons. This down here is just the number of protons. So if you want to figure out how many neutrons, simple. Okay. Take the mass number, the top number, subtract the atomic number, and you get the number of neutrons. So 1 minus 1, this basically means that the neutrons for this one is 0, 2 minus 1 is going to give you 1, 3 minus 1 will give you 2. Okay, elements on the periodic table. Every periodic table will give you at least 3 things. Okay, and one of those things does not have to be the name. Okay, so you will see 3 numbers listed. Okay, the top number, or it may be on the bottom someplace, but this has to be a whole number. Okay, that's the atomic number. You obviously have to have the symbol for the element. Names can change according to languages, but the symbol will always be the same. And the bottom number is what's called the atomic mass, and the units are in AMUs. Okay, notice, we don't have the mass number. The mass number is not the same as the atomic mass. Okay, so what's the basis for this atomic mass unit? Okay, 1 AMU is exactly 1/12 the mass of a carbon-12 atom. Okay, carbon-12. It's basically carbon has atomic number 6, mass number 12, so that means you have 6 protons. Neutrons is top number minus bottom, 6. Electrons have to be the same as the protons. Okay, so carbon-12 has to, if exactly 1/12 of the mass of carbon-12 is 1, that means carbon-12 weighs exactly 12 AMUs. Okay, now the mass of every other element is compared to the mass of carbon-12. Okay, so if something like carbon-13 is 1.083613 times heavier than carbon-12, that means you know carbon-12 is 12 AMUs. Carbon-13 is that many times heavier, so that means carbon-13 has an atomic mass of 13.003356 AMUs. Okay, now the average atomic mass. Okay, carbon has 3 isotopes, or 3 nuclides. Okay, carbon-12, which you know weighs exactly 12 AMUs. Carbon-13, we just calculated, weighs 13.003 AMUs. Carbon-14, 14.003 AMUs. Okay. Now, if you average these masses, like the term average atomic mass kind of tells you, okay, you'd expect to be 12 plus 13.003 plus 14.003 divided by the number of isotopes you had, 3, and it should come out to be 13.002. So this is what you would expect to see on the periodic table for the average atomic mass of carbon. Okay? But when you look on the periodic table, it's 12.011. So why? Where did this 12 come from? Okay. Well, the average atomic mass of an element, this is what you see on the periodic table, is not just simply the average of the weights of each isotope. It is the weighted average. Okay? Not every atom in that sample has the same mass. Okay? So how do you figure out the age of people in the class? The average age of people in the class or average age of people on the campus. You don't just take the number of people or the age of each person, add them up and divide by the number of ages. You divide by the number of students. Okay. So, how do you get the average atomic mass? Simple. It's the sum of the mass of each isotope times the percent abundance. Okay. Here's an example. Carbon-12, 98.90%. So, you would expect that the average should be really close to 12. Okay. Carbon-13, 13.003 and only 1.10%. If you took a mass of just pure carbon atoms, 98.90% of them would be carbon-12. Okay. Carbon-14, pretty much the percentage is so small in terms of decimal places, it's not noticeable. Okay. So how do you calculate the weighted average? Take the mass times the percent. Make sure you change this into a decimals. In other words, divide your percent by 100. Okay. Add to it the mass of that one, the second isotope, times its percent, times the mass of the third isotope times its percent, which is 0. And when you add these all up, you come out with 12.011. Okay. So that is where the average atomic mass came from. Okay. The atomic mass of most elements will usually give you an idea which is the most common isotope. Okay? In other words, when you look at the mass number, if it's whatever it's closest to, find the nearest whole number, that should basically tell you which isotope is probably going to be the most prevalent. Now here's your review question. Looking on a periodic table, hydrogen has an atomic mass of 1.0079 AMUs. So, how many of the 3 isotopes of hydrogen will have a mass of 1.0079 AMUs?